Hello, this is Jack Jackson. Today we're going to be talking about systems of equations of linear type. So what we're talking about here is taking our idea of systems of equations where we have linear equations in two variables and talk about linear equations in 3 or 4 or 5 variables, multiple variables. Or maybe we should call these linear type equations. So we're going to break this video up into 4 parts. The first part, we're going to talk about a graphical interpretation of systems of linear equations in 2 and 3 variables, forms of linear equations in multiple variables, and then visualization of possible solutions for 2 and 3-dimensional linear systems. In the second video, we'll talk about how to algebraically solve systems of linear equations by the technique called elimination with back substitution. And so that will be basically just generalizing our technique that we've already used with elimination with back substitution for 2 variables, and we're going to extend that to 3 or 4 or 5 variables. In video 3, we'll talk about how we can use matrices to represent linear equations as systems of linear equations, and then we're going to use a technique of manipulating the matrices that it's going to correspond to more or less to the elimination technique, and this is called Gauss-Jordan elimination. So we'll learn how to solve equations that way. And in the 4th video, we'll do a few applications that lead to linear equations. So let's start by considering something here. If I consider the equation x equals 3, what is the solution to that? Well, it kind of depends on whether we're talking about solutions in 1, 2, or 3 dimensions. So if we're talking about a one-dimensional solution, we're talking about a set of points on a number line that make that true, which of course is only one point. X is just an element of the set 3, or in other words just x equals 3. It's a single number, it's one single point on a number line, and you can see it graphed there. But we can also think of this in 2 dimensions as a relation that tells us something in 2 dimensions. And so this would be the set of all points x, y such that the x coordinate is 3. The y could be anything. So we could write that as saying x, y is an element of the set 3 comma y such that y is any real number. And if we graph that, we don't just get a single point, we get a vertical line, and you can see the red line graph there in the plane. So it's a vertical line in a plane. But we can also extend this another dimension if we want to. We could have a 3-dimensional solution. So it's a set of ordered triples, x, y, z. Now think about how you might do ordered triples. If we want to graph a number on a number line, we locate it on the number line. That's a one-dimensional thing. Every real number corresponds to a point on a number line. To find points in the plane, we need ordered pairs. So, for example, the point 3, 4 says you go to the right 3 and then up 4 here. And you get to this point right here where my cursor is moving around there. Okay? Now, how do you find points in space? Well, you need another axis. So the x-axis is a number line. Well, the y-axis is another number line perpendicular to the x one. And the z-axis is another number line perpendicular to both of those. So it'd be coming out of the screen towards you. So if we wanted to find the point 3, 4, 1, we go the right 3, up 1, and then towards you 1. So if we have the set x equals 3, but we have that in 3 dimensions, it would be all ordered triples x, y, z, such that the x is 3. So we could write that as x, y, z is an element of the set 3, comma, y, comma, z, such that y and z are real numbers. Y and z are any real numbers. And this turns out to be a plane in 3-dimensional space. It's parallel to the YZ plane. And you can kind of see it sort of illustrated here. Of course, anytime we take a 3-dimensional object and represent it on a flat piece of paper or a computer screen, we lose a little bit there, but you can get an idea of what's going on here. So here's your x-axis is labeled here with the red here, and the y's are labeled in green and z's are in blue. Actually, the origin is right in the middle of this box that we see here. If you notice, the x's here. Here's -1, here's +1. So here's x equals 0 right here. And then y equals 0 is here, and z equals 0 is about here. So somewhere in the middle of this box is the origin. And if we go to the right of the origin 3 units, we get this plane here, because every one of these is to the right 3, and it could be going up or down, in the z direction is, whatever we want to go, and back and forward in the y direction, whatever we want to go. And so that is a plane there. So if we want to generalize this a little bit to not just vertical lines, but lines in general, in 2 dimensions, we have a general form that we could write ax plus by equals c, where a, b, and c are constants, and of course x is our input variable, y is our output variable. Okay, now that particular form is not super useful, but it is a form that we can see. Another form that we can use, that we've used before, is a point-slope formula. It says y equals m times x minus x1 plus y1. So x1, y1 is a point, and m is delta y over delta x. That is the slope. And the graph, of course, is a line in a 2-dimensional plane. Well, we can generalize this to 3 dimensions. Ax plus by plus cz equals d, where a, b, and c and d are constants. Well, it turns out that that's not a line in 3 dimensions. What that actually is a plane. So most of the time people will call this a linear equation in 3 dimensions, but it's not really the equation of a line, it's the equation of a plane. So I'm going to call it a linear type equation. But it's also correct to call it a linear equation, even though its graph is not really a line, its graph is really a plane. But it's a generalization of a linear equation that we have in 2 dimensions. So we just added a z term, which has just got a constant times z. Notice in both the 2-dimensional version and the 3-dimensional version, we just have a constant times x, a constant times y. We got it equals a constant. The x's are the first power, the y's are the first power, z's the first power. No multiplying or dividing by x or y or z, other than to multiply x, y, and z by constants. So that's what's meant by a linear equation or a linear type equation. You can have a point-slope kind of formula for linear equations in 3 dimensions, that is, equations of a plane. It's z equals a times parentheses x minus x1 close parentheses plus b times parentheses y minus y1 plus z1. If you look, that's a very similar form that our point-slope form up here. And this does go through the point x1, y1, z1. Notice when x is x1, this term goes away to 0. And when y is y1, this term goes away to 0, and you're left with z equals z1. And so that does go through the point x1, y1, z1, that should say. You know what? Let me fix that real fast. This should have a third coordinate, z1. Like that. There we go. Should have 3 coordinates, x1, y1, and z1. Okay? And it does have sort of like a slope to this too. A is like a slope in the x direction. So it's z's your output variable. Your inputs are basically ordered pairs of both x and y. Okay? And so the output variable, delta z over delta x, if delta y is 0. You can kind of see that here. If delta y is 0, y and y1 are the same. So this term right here with the b goes away. And so you've got z equals a, x minus x1 plus z1. Subtract z1 from both sides, you get z minus z1 is a, x minus x1. So that's basically delta z equals a delta x. So a is delta z over delta x. If what? If the delta y is 0. And similarly, b is sort of the slope in the y direction, because if you let delta x be 0, then b is just delta z over delta y. So what that would mean if you're in the plane is like this. So here's, you get a graph of a plane. You can see an example of one here. Okay? Because that's what it is. It's a plane in three-dimensional space. If you're at some particular point here, x1, y1, z1 in the plane, let's say you're right here, then this one, if you don't go in the y direction anyway, you just point in the x direction and move over a little bit in the x direction, that a is basically the slope in that direction, how far you're going up in the z direction, or down if it's negative, divided by how far you went in the x direction. And similarly, in b, you would take that point and you move in a y direction only. So we can see that when we add another variable, we no longer really get a line, but we get something very similar. So these are still called linear equations or linear type equations. So we'll call any equation of this form a linear equation or linear type equation. Ax plus by equals c, or ax plus by plus cz equals d, or aw plus bx plus cy plus dz equals e, or so forth. Sometimes we'll take these same things and we'll rewrite it a different way. We'll call the coefficients by some letter, say a, and then they have subscripts. And your variables, instead of calling them x, y, and z, we'll call them x1, x2, and x3. So sometimes you'll see equations written this way. a1x1 plus a2x2 equals a constant. a1x1 plus a2x2 plus a3x3 equals a constant. That's a three variable equation, linear equation. A four variable equation would be a1x1 plus a2x2 plus a3x3 plus a4x4 equals a constant. And then you see a five variable version. And you could have an n variable version of this. So you'd have n dimensions. Now, it's a little harder for us to think of what these things are graphically once we move on beyond 3 dimensions, but we can still generalize this concept. Now, let's think back to what we have in 2 dimensions. If you have two different lines, then there are really only two possibilities. Either the two lines are parallel and there's no intersection, so there's no solution to that system of equations that's represented there, or the two lines intersect in one distinct point, right here in this case. You can see my cursor moving there. So, one single point. Now, of course, you do have a degenerate case where you actually have the same line twice also. But they wouldn't be distinct lines then. And so if you have planes in 3 dimensions, if they're distinct planes, you basically have the same situation. You could have parallel planes. This is maybe a little bit hard to see here, but here I've graphed parallel planes here in this software. Or a good way to think of parallel planes, can you think of some just in the room there, wherever you are, assuming you're not outside somewhere listening to this? Where would be something that might represent parallel planes? Did you maybe come up with, say, the plane containing the floor and the plane containing the ceiling? Those might be parallel if they're flat ceiling. Now, if you've got a vaulted ceiling of some kind, that may be different. Okay, but you might have parallel there, or maybe the front wall and the back wall of the room might be parallel. Okay, and I'm talking about just those walls, but it's the whole plane that contains them. Now, if you have two planes that intersect, where the two planes are actually different planes, then their intersection is going to be a line. And you can kind of see that in this picture where I've got graphed two planes, and you can see the red line there is where they intersect. And so they intersect as a line that's in space. It's not necessarily in the XY plane, but it's in space somewhere. So thinking back to the room, where could we have intersecting lines? Oh, say maybe one of the walls and the floor. Okay, that would intersect in a corner down across, going across the room. That would be a line, part of a line. Of course, if you do the whole planes containing the wall and the floor, they would intersect in a line. Or maybe two walls that meet. There would be a vertical line going up there where they meet in the corner. So if you have three planes in three dimensions, maybe unique, maybe not unique, which of course would be a system of three equations with three unknowns, it's a linear type system, there are actually four different possibilities. There's no intersection. Now certainly if two of the planes are parallel, then there's not going to be an intersection. Okay? But it is possible to have no intersection even with no two of the planes parallel. So look at this picture here, if you can kind of see what's going on there. Notice that we have three planes, and basically any pair of those two planes do intersect in a line. But the three lines formed are all, any two of those lines are parallel to each other. So, for example, the first two planes intersect in a line, but that line is parallel to the other plane. So there's no intersection of all three. Okay? So that's sort of a special situation where there's no solution. Another one I don't have graphed, but it's also a no solution case, is when two of the three planes are parallel, or perhaps even all three are parallel. No solution. Another one that's sort of the just right case, that is when they intersect in one point. So think about it a minute. The two planes intersect in a line, and that line could pierce through the third plane in a single point. And that's illustrated in the upper right example. So the red dot is the only point that's on all three planes. Okay? So we would call a system of equations that gave us no intersection an inconsistent system, and we would say it has no solution. If it intersects in one point, we would say that system is consistent and independent, and we get one solution. If it intersects in a line, it is possible for two planes to intersect in a line, and then the third plane actually still contains the same line, so that all three planes intersect in a single line, and that's illustrated in the lower left. In this case, we have infinitely many solutions, but they're not just any solutions, they're infinitely many solutions along that particular line. And we can actually, in that case, if it's x, y, and z are your variables, you can basically solve for x and y both in terms of z. So let z be anything you want. Let z be all real numbers, in fact, and then we have x and y given as functions of z. Of course, then the degenerate case is you don't really have three different planes. You actually have the same plane three times. And of course, then the same plane is going to intersect with itself as the whole plane. And of course, that gives you an answer of the whole plane. And that's sort of like the case where we had the same line twice for the two-dimensional case. And of course, the best you can do here is maybe solve maybe in that form that we had back before, so where you solve for z. Maybe this point slope kind of formula might be the best you can come up with, or something similar. Okay, so that's going to be the end of our first video. We're going to come back now in the second video and talk about solving systems of equations by elimination with back substitution.